Hello, everyone. Today we're going to be talking to you about hypersonic inlet design and some of the considerations that need to be taken into account. My name is Mark Gallus.
And I'm Brian Wintermantle. So today, to outline the presentation we're going to give you, we're going to introduce inlets and what are hypersonic inlets. And then we're going to discuss the different difficulties in designing these inlets. We're going to go over recent advances in inlet design. We're going to go over types of inlets that exist and recent advances in hypersonic inlet testing and design.
So with that, we're going to jump into an introduction, kind of discuss hypersonic inlets and how they work.
So what are inlets and what is their purpose? So in a hypersonic scramjet or ramjet, in general, inlets are designed to capture and compress air and pass it along into the combustor. In general, for these machines, more air coming in inlet means more mass going through the engine, which means a higher thrust the engine is producing. So it's always good to have more air going through. So it's important to consider the inlet design. Shocks are used to reduce airflow speed prior to entering the combustor in the inlet, which is important because ramjets require subsonic combustion, so the inlet must reduce the airflow velocity to allow for combustion inside ramjets. And so they do this by the manipulation of shocks using various blunt bodies and sharp bodies to reduce the airflow speed. Some have fixed geometry inlets, which means they are designed for specific Mach numbers and have Mach number constraints.
So now on to some of the difficulties of designing these hypersonic inlets. It was just touched on in the last slide. There's typically a free stream Mach number that they are designed for, and they're designed for this specified speed. This has to do with the boundary layer creating a separation zone, which can reduce the airflow in through the inlet, which is shown on the right. This can choke the flow. Another thing that can happen is you can have the normal shock translating upstream, which can exceed design parameters, causing unstart. Uh, and so what you have to do is you have to balance the drag and the airflow capture. Having a bigger cowl means that you can have more air going into the combustion chamber, which means more thrust. But this also means that you have more heating and more things you have to deal with in that sense.
So there are different types of inlets in the sort of scramjet ramjet field. Two main types of approaches to creating your inlet include the external compression inlets, which use an extended cowl to compress the flow prior to entry into the inlet itself. And then the problems that ensue with the external compression inlets are that the extended cowl has a high amount of drag. The internal compression inlets compress the flow after it enters the intake. And problems with that is that they generally require a lot of overspeeding to start.
So there's two different types of inlets that are really focused on. And the first is the fixed geometry inlet, where the lip of the cowl is fixed. It's designed to self-start at a certain Mach number. It's much more simple and lightweight compared to the other option, and it has a very limited operational window in terms of velocity. The other option is a variable geometry inlet, which is, as it sounds, allows the cowl lip to be moved. And this allows for the performance to be tailorable over a larger range of Mach numbers. The How it does this is by changing the geometry at the start of the inlet, but there is additional mass and complexity from the actuators and sealing and overall the mechanics of having that system involved.
So now we're going to go over recent advances in hypersonic inlet design and some of the things people are doing in order to try to experiment with increasing their efficiency and performance.
So starting with geometry considerations, a lot of the different hypersonic inlets that we've seen in class have looked rectangular, I'm sure you've noticed. And so NASA was looking at the transition from a rectangular or triangular cowl to an elliptical or circular combustion chamber. And they were doing testing at Mach 4, even though the inlet was designed for Mach 5.7. They also tested at Mach 6.2. And the goal of this testing was to kind of verify and look at the rectangular to elliptical shape transition. They wanted to test the starting and back pressure limits to see what caused the engine to unstart and what range it was able to run in. And this required, one important note is that it required side spillage holes to self-start at Mach 4. Otherwise, the flow would choke at the inlet. And then they also showed in conclusion that the rectangular to elliptical inlets can work with a fixed geometry over significant Mach number ranges. And just going back to the first bullet, you can see they were able to run at Mach 4 all the way up to 6.2, which is actually a pretty big speed range for a fixed geometry.
So another recent advance is from one of the NAIAA paper is they're starting to create these things known as detonation wave ramjets. So this design allows for the shock waves themselves created by the inlets to actually create the ramjet combustion. And so in these, the detonation wave ramjet uses shock-induced combustion wave to combust the pre-mixed air and fuel. Different inlet designs are used to create the things you can have using normal shocks, oblique shocks, or many different types of closed external and internal compression inlets. And so the shock wave compression waves raise the temperature and pressure of the gas mixture to the ignition point themselves. And the shock wave can either be normal or oblique, can be planar or asymmetric, and it can be generated by gas dynamic processes, by wedge, or by blunt bodies. Whatever the way, what it does is it creates the combustion without having to be ignited. So there are several advantages that detonation waves inlets have over scramjets. And so one of the advantages is that the shock component of the compression process provides additional large compression and high temperatures required for rapid combustion, which increases combustion efficiency. The compression needed in the inlet is a lot less than that of the scramjet, and so the losses involved with the inlet deceleration are a lot lower. And one of the bigger considerations is that the small area of combustion, due to the fact that the wave itself is combusting it, allows you to shrink the combustor of the ramjet to be very short things, which allows for a shorter and much more lightweight engine than the scramjet. But however, it does come with a major disadvantage that the detonation wave ramjets have a lack of static thrust. And so the implementation of detonation wave ramjets on actual vehicles do face some technical challenges. Number one, the stability of the detonation waves that are going to be put on a certain vehicle would need to be established for all variables of your engine performance, such as velocity, pressure, temperature, and make sure that those waves remain stable, because that is what's creating that combustion. Without the compression, there's no thrust. The fuel must be mixed upstream of the wave, and so you need to establish how much losses you're going to get from mixing that fuel upstream. The ignition of the fuel at the ingestion point has to be minimized or avoided completely, because that would create a combustion prior to the combustion wave itself. Then also boundary layer separation that is caused by the wave itself has to be controlled in order to maintain inlet feasibility, and you need to calculate estimates of realistic propulsive performance estimates for the detonation wave ramjets before actually being able to use them in reality.
So next, a new inlet design approach that we found pretty interesting. The criteria chosen for this paper was shock on lip conditions, which maximizes the capture area and minimizes the inlet length. The performance analysis they did was using CFD. They did that both in 1D and 2D inviscid and viscous effects to see how they would impact performance. And then they use gas dynamics relations for turning angles, internal external ramp angles, and shock angles in order to parameterize the problem. Um, Basically, what a shock on lip condition is all the external and internal oblique shocks are made to meet at a single point in the design phase to maximize the capture area and minimize spillage losses. And kind of the takeaway from this slide is looking at that image in the bottom right, you can see all the different parameters that go into designing an inlet with these conditions in mind. So it's a very complex problem. Next slide, please. So just a little bit more about that. So they considered the air to be an ideal gas, and they solved 2D Navier-Stokes equations with CFD. They also assumed that the surface temperatures were held at 1,000 Kelvin, which from our talks in class, we know that it can get a lot hotter than that in reality, but for this analysis, they held it at 1,000. On the right of the slide, you can see the experimental versus the CFD results and how they match up. And one important takeaway that they pointed out in their paper was that the 2D simulation did not match the 1D analysis. So even though the geometry was chosen for the shock on lip conditions so that everything would meet at one point, the introduction of the second dimension caused deviations for the viscous analysis. They believe this is due to the boundary layer effects and the shock wave with boundary layer interactions. Um, and kind of the main takeaway they had is that design gets much more complicated and much harder when dimensionality increases. So that's why you see a lot of papers that are doing 1D and 2D analysis and only a few that are doing three-dimensional analysis. Next slide.
So
Um,
another new inlet design would include the 3D sidewall compression inlet hydrogen scramjet. So they use a numerical approach to solve the compressible Reynolds average Navier-Stokes equations, supplemented with a finite rate chemical reaction model for the combustion of hydrogen fuel and air. And with this, they analyzed the flow structure, the mixing, combustion efficiency, and static pressure distribution. They found that intake sidewalls are found to have a large impact on the flow structure here, hence the combustion region forming asymmetrical separation bubbles. The complicated shock train system induced by the longitudinal lateral compression actually impacts the combustion region upstream of the injection and leads to standardized asymmetricities in the flow. And this entire thing has shown that the inlet flow distortion has better performance of mixing and combustion augmentation to some extent by comparing the degree of improvement of mixing and combustion efficiency.
and then next paper we found on the demonstration of a TBCC, looking specifically at the transitional mode between the turbine and the scramjet. The goal of this paper was to address key hypersonic combined cycle engine issues, including dual integrated inlet operability and performance issues, unstart constraints, distortion constraints, bleed requirements, and the control of the actual inlet. Looking at mode transition sequence elements caused by switching between the turbine and the ramjet scramjet flow paths, and then turbine engine transients and the associated timescales during those transitions. So looking at, how quickly does the inlet move and transition between the high Mach turbine and the scramjet, and what effect that has on performance. Just continuing from that, so from takeoff to Mach 4, both inlets were actually open, but the primary thrust comes from the turbine. The rationale for having both engines open, even though the ramjet isn't really going to be producing thrust, was because it was necessary in order to fill the nozzle and reduce the base drag on the system. One of the requirements of this, though, is that the turbine has to be able to reach Mach 4, and your scramjet has to be able to start under Mach 4 because that was the transitional period. Once at Mach 4, though, the airflow is opened for the scramjet, and the turbine is put into a low mode with an almost closed inlet, similar to during the takeoff phase. Success was determined if smooth transition occurred between the two. So when the flow is diverted from one flow path to the other, there is no unstart or buzz. And just so you know, buzz is when the shocks oscillate and move back and forth within the system. And this paper was in phase 3, which was a demonstration of the control loops and how they would actually actuate it. Uh, testing is going to be required, where they move the mass flow plug and insert an actual Mach 3 capable turbine. And for that, they're using a Williams modified WJ38 for phase 4 of this research, which is shown on the next slide. So on this slide, you can see the turbine, and then this is the nozzle facing towards us.
All right, so to conclude this presentation, it turns out it's very hard to model 3D inlet geometry. So most analysis that end up being done are within a 2D environment. Inlets are typically designed for a design Mach number, which they are specifically designed to run at. And many potential potential improvements can be made can be implemented to future scramjet and ramjet designs to increase their efficiency or increase their combustor efficiency or to increase the compression rates and to decrease losses. And so we can break testing down to small accomplishable tasks in order to slowly increase the abilities of scramjets and ramjets within the future. So to conclude, get your PhD in inlet design because there's plenty to do.
Thank you all so much for coming. Our references are shown on the next slide if you want to learn more about inlet design.
Thank you very much.